Okay, thank you so much, and thank you to all the organizers. In the spirit of this conference series, I have too many slides, so without delay, let me dive into this. I really want to present this talk as an umbrella talk to give shout-outs to my colleagues who are also here and who are part of our team at MIT and our collaborators. So there will be Peter Hagelstein's talk on theory later, Ben Barrow's talk on our experiments and related experiments, and then Jonah Messenger on isotopic analysis. So this research that we're doing is part of this new ARPA-E program on low energy nuclear reactions. Here's just a part of the press release to announce this. And we went ahead and put on this preprint server a concise version of what our proposal, the proposed research was about. And I want to highlight that the proposal process was driven by these 4 early career researchers. The average age is 32. I'm not going to mention the variance, but we're all below 40. And it's heavily inspired by the work of Peter Hagelstein. And the ARPA-E team in various communications emphasized that LENR may be an ideal form of nuclear energy, but there's also the situation where there's a stalemate. The field is kind of stuck in the sense that people would like to see more high quality work, but there's also not enough funding, as you all know, and so how to overcome this. The goal really is, and that's where I think we're aligned, if there is potential for technology, then we want to bring the might of the scientific enterprise to bear, such that there's access to regular funding channels and there's an influx of people with relevant expertise to work with all of us together on these kind of questions. And so the way scientific fields form and evolve, I've sort of broken down here very briefly. First this question, is there a new phenomenon, is there a new effect? For instance, what the ARPA-E communications called a novel class of nuclear reactions. And then the next step would be, what are all the key variables to cause the effect, and then eventually you get to the mechanism. When you want to engage in technology development, you need to get to the sort of second and third stage, but often it's necessary to unambiguously establish the reality of this new effect or new phenomenon in order to cause an influx of funding and resources. And that hasn't quite happened, otherwise we would have a lot more people at these conferences and doing this kind of research, given the potential significance of it. And so we all know that there have been kind of problems with, I would say, bad faith actors that have tried to maybe smear research in this field and so forth, but there are also good faith people who have looked at this field and who walk away confused. And so I think that is rooted in the fact that there's still too much ambiguity about the results to date. At least too much ambiguity for what it is that contemporary science can deal with. And so in our discussions with the ARPA-E folks, there arose this need for having irrefutable evidence for a new class of nuclear reactions to overcome this stalemate between funding and the quality of research. And that kind of sets up the frame for this ARPA-E program. And so then we can look at all the various kinds of experiments and experimental outcomes that have been proposed and reported in this field to find what is going to be a good candidate for a kind of reference experiment that provides irrefutable evidence. And in my view, there's really 2 kind of categories for irrefutable evidence. One is excess heat, far beyond chemical levels, and the second is unambiguously nuclear products or products of nuclear origin. With excess heat, there's always a headache that you have to engage in extensive characterization of your calorimeter, and you also need to have reliable accounting of the mass and energy in the closed system. And so that can be very difficult to do. So we chose to focus on products of nuclear origin, and we're well aware that they may not be present in all LENR experiments, but they certainly are present in some LNR experiments, and so we consider that to be a good starting point to get this field to the next step in this sequence of critical events in field formation. So these were then the criteria based on which we chose our project. We wanted to maximize the chances of replicating an effect, and then also maximize the chances of identifying what we observe as irrefutably anomalous, if it is so the case. What was not an explicit criterion was the direct suitability for technology development. That of course, we all have that in mind, but that could happen as a separate step further down the line. And it also didn't need to be the most spectacular result, as long as it's scientifically sound and rigorous. So what we ended up with focusing on is these gas-loaded palladium and titanium samples that have been treated with low-power laser radiation and in some cases sample heating. And the observables are neutron and or gamma bursts and also low Z element formation, which we expect to contain isotopic shifts. So it was a very basic general picture of this kind of experiment would look like that. So you have a laser stimulating a metal hydrogen sample in a chamber into which deuterium is introduced. The sample absorbs the deuterium, you get a metal hydrogen system, and then you get laser stimulation, and we expect neutrons or gammas, depending on the experiment, as an outcome. And so if we look at the lattice itself, so on a high level, the hypothesis would be that we then have our metal hydrogen, so again, palladium deuterium or titanium deuterium sample, and you get certain clusters of high proximity deuterons, and you also get dynamics in the lattice induced by the plasmons and phonons caused by the laser, and then you have an accelerated DD fusion that drives also the fission of some of the metal lattice nuclei. So that's sort of the hypothesis, this combined fission process on the high level. I'm going to go a little bit in more detail later. So the motivation for this comes from the LNR literature. So we've, and again, I'm going to go through this quickly. I encourage you to look at our preprint, where we can spend more time on this. But these are papers mostly in peer-reviewed journals that have reported, in this case, bursts of neutrons and gammas. And the highlighted ones included laser irradiation and more benign pressure and temperature conditions. And I'd like to highlight here Uchikoshi 2020, a thesis by a Japanese doctoral student, which is, again, a similar setup as what we've seen before. Palladium deuterium sample irradiated by laser, a neutron counter detector nearby. The upper graph shows the absorption of the deuterium gas by so the pressure drop, so the absorption of the deuterium gas by the palladium sample, and the lower graph shows over time in dark blue these bursts of neutrons against background. There's a similar configuration by Dukov et al. From the early 1990s. This involves a titanium deuterium sample. Here we added in red the laser being switched on. So you see the temperature rising as the laser is switched on, and then here in this graph the authors highlighted where the neutron and gamma bursts occurred, and so you see a vague correlation with the activity of the laser. And then there's Mastro Matteo, a series of experiments by Mastro Matteo, and also a similar type of chamber with palladium deuterium. And in his most recent papers on this series of experiments, he also reports a burst of neutrons. So the y-axis here is neutrons per minute. And so then there's the second group of experiments, and to some extent there's overlap, where morphological changes were observed on the surface of such samples. And these morphological changes, when elemental analysis was conducted, revealed some purported elemental anomalies, low Z elements. And so there's Narcisi, 1998, again, a chamber, in this case, with a palladium wire, laser irradiation, and when these spots were found and observed, in this case, on this spot, there was iron found, and you see in the upper spectrum just a part of the sample that didn't have a spot on it. And then Jean-Paul Bivarian did variants of this experiment, and here you see also over a superposition of 3 spectra on the top and 3 at the bottom ones at the side of these morphological changes and the bottom ones on besides, and you see these low Z peaks at the side of this spot. And so we had a bit of a deep dive, and we also found that these peaks correspond to these low Z elements. They correspond to pairs of fission daughter products of different palladium isotopes. So that kind of motivates this hypothesis of induced fission of palladium isotopes in these kind of samples. So in our campaign then, we plan to have a master chamber and several smaller chambers where we can vary these variables here to replicate as best as possible these different experiments that I showed you, this class of experiments that I showed you. And so this is kind of the master chamber, the most comprehensive version of this. Again, you can look at our preprint to look at it in more detail. And then we have these ex situ measurements, then we have the treatment with a laser and in situ measurements, which are mostly radiation detection, and then we have these ex situ measurements, sample mapping, elemental analysis, and isotopic analysis. We've done some preliminary experiments already, most of them at Ben Barrow's lab, again, he will present later at this conference. And just to walk you through briefly the kind of measurements we're doing, includes sample mapping. Here are some results that some preliminary results from Ben that he presented at last ICCF conference, where he, in a similar configuration, observed also these spots with, in this case, iron and nickel peaks. But we want to become really rigorous about this and develop like best practices for isotopic analysis. We want to dig into these spots and see through a combination of neutron activation analysis and TOF sims whether there are isotopic shifts in these or unnatural isotopic ratios for these purported elemental anomalies. So Jonah will have a poster on this. We're building a lot on George Miley's work on combining neutron activation analysis and TOF sims. So I'm just giving you a glimpse here. Our colleague Nicola Galvanetto has started working on developing sort of a rigorous framework for statistical analysis of neutron detection data and identifying bursts that are statistically significant. So that's just a glimpse of his work here. And then I want to just end by walking through the hypothesis in a bit more detail and kind of also helping to set up Peter's talk. So the framing that Peter has taken to this, as well as other leading theorists like Julian Schwinger since the early 1990s, is to look at the fusion reaction as a state transition from a higher energetic state to a lower energetic state that is hindered by the reconfiguration of nucleons that has to take place. And so here's from another paper. I'm going to skip through this. There's animations on how these kind of fusion reactions take place, in this case for astrophysical, physically relevant fusion reaction, and then there's also animations of how these state transitions can be visualized at the atomic level. So a state transition at the atomic level is then the reconfiguration of electrons. And with this setup, we can sort of postulate a spontaneous fusion rate, which Kunin and Naunberg has estimated in deuterium gas at room temperature at 10 to the minus 64 per second per deuteron pair. If you're in a lattice, you have the electron background from the metal, so you're getting close to proximity, and so you have a higher rate. I think consensus is that you get 20 to 25 orders of magnitude enhancement through this. including the kind of dynamics, classical dynamics that you have from the neutrons. But still, this spontaneous fusion rate would be incredibly slow. And so if you were to hope for a incoherent coupling of deuterium fusion and palladium fission, it would be theoretically conceivable, but it would be hopelessly slow. And so it would be basically this process of deuterium-deuterium fusion. 1 million of those roughly would lead to a photon. The photon would be absorbed through photofission by a palladium, and then lead to the palladium's disintegration. So that's what our hypothesis is, but much enhanced, much accelerated by quantum coherent process, which again Peter will talk about more. So yeah, if we just look at the timescales, screening gets you from the roughly 10 to the 60 to 10 to the 30 years that you have to wait for your deuterium nucleus to spontaneously fuse. But then there's this gap. Okay, we want to go further, and the argument here is, again, we go further through this excitation transfer, this coupling of a fusion reaction by simultaneously exciting a resonant lattice nucleus, like a palladium isotope, that then induces a fission reaction. This is well known in the larger quantum engineering community as a quantum state transfer, which can be induced by activating a coupling between two-level systems. We have previously shown these mechanical analogs. So if you have an isolated two-level system, the occupation probability can be simulated through the energy of that system. But if you have two-level systems or two oscillators, the de-excitation can be accelerated, and if you have a stronger coupling, this state transfer happens even faster. So where do the couplings come from between the nuclei? Well, you have phonons, you have plasmons that can generate phonons or convert to phonons. So when you have laser stimulation of a sample, you get something like what's illustrated here. This is phonons in germanium, so you can visualize this as sort of the lattice kind of vibrating, and so you get these nuclear states that are coupled to shared oscillators. And so the mechanical analogs are helpful as a first approximation, but the quantum way involves these delocalized excited states as intermediate steps. And what's really interesting about this is where you get this phenomenon of Dicke enhancement. So the more nuclei or more two-level systems that participate in these delocalized excited states, the faster the process can be. And so that introduces this Dicke factor that describes the acceleration. And so there's a nice paper in Nature Physics that shows the acceleration of nuclear decay of the nuclear state transition from iron 57 14 keV to ground state as a function of the participating nuclei. And so that's the kind of enhancement that we're very interested in. So this is based on Peter's work, putting together Hamiltonians that describe these kind of dynamics and then allow to derive a transfer rate, which then corresponds here. We have estimated 10 to the minus 18 per second as the transfer rate from palladium, from the deuteron pair to a palladium nucleus. And so you see these Dicke enhancement factors in here, and then we've identified here the intermediate variables, which then can be also connected to the independent variables that can be controlled in the experiment. So that we view as the beginning of thinking systematically about engineering these kinds of systems. And so again, rather than the incoherent coupling of fusion and fission here, this represents this coherent coupling where both the deuterium to helium-4 transition is accelerated and also the excitation of the palladium nucleus. And in this case, if you just transfer 23.8 MeV from one DD fusion reaction to a palladium nucleus, you get neutron emission, you get asymmetric fission. But it's kind of well known in the nuclear molecule literature that if you apply higher and higher energy to these nuclei, then they turn into more symmetric type of nuclear molecules and split more symmetrically, and then you would expect more symmetric type of fission and more like these low Z fission products that have been observed or reported. And actually in the atomic level quantum literature, this is known as quantum ratcheting. So you're kind of ratcheting up by pushing, in this case we have multiple fusion reactions that ratchet up a palladium nucleus to a higher state that then makes it break apart. Okay, this is situated, we situate this in this emerging field of quantum energy science. So there's another preprint of our group that I can refer to here, where we situate this kind of thinking in what's now called quantum solar engineering, quantum batteries research. There's also this emerging field of quantum superchemistry, where people also use these collective states, these sticky enhancement effects to accelerate chemical reactions. So we want to use them to accelerate nuclear reactions. And so to conclude, I think what we'll see is this kind of convergence of both these bottom-up efforts where quantum engineering moves more and more into the energy space, and then also these top-down efforts where I think these existing programs that we have will establish more and more to which extent these claimed anomalies are real. And I think at the intersection of that is the potential for a new engineering discipline, which might be called quantum enhanced nuclear engineering. So we see ourselves as part of a collective effort that hopes to catalyze an important phase change in this field. This path is informed by decades of work from this community, so thank you. It's also based on the enormous effort by Peter Hagelstein, who identified mechanisms that both explain a wide range of anomalies that connect seamlessly with the established physics and that match observations quantitatively. So we're committed to conduct science at the highest standard, publish all key results in a timely manner, and we reject ill-informed secrecy and making strong and definitive statements without commensurate evidence. So if you have some Blenner experiments with purported neutron gamma emission or elemental anomalies, please get in touch with us. We'd like to work with you. And we want to also contribute to the community, the development of best practices for nuclear particle measurements, neutron gamma measurements, and rigorous statistical analyses, and also rigorous isotopic analysis. So thank you very much.
Thank you. And now I think Florian is ready for questions.
Hi Florian, thank you for your talk. Are you aware of Shishkin's, Korol's and Dobovik's concept, which I actually shared with Jean-Paul Barbarian with that laser spot on the, I think it was nickel or whatever it was, titanium. The ambient neutral magnetotor-electrical radiation, which is exactly equivalent to Ken Shoulders' EVOs, are captured and guided from the environment by laser light onto material, and they argue that this is the cause of the reaction. And just to add to that, they say that this is essentially, in common parlance, static electricity is gathered by the laser light, but it's in a neutral form cluster. And to add to that, have you considered using an ionizer in dry air using the laser to see if it changes the reaction rate? And I'll tell you why I say that. In 2015, in February, when I visited Alexander Parkhomov in his apartment in East Moscow, he had the mother of all ionizers in the room where he was conducting his experiments.
Yeah, so I'm not aware of the first group of experiments that you mentioned. I'd be interested in talking about them more. On the second question, we're focused on staying as close as possible to these reported experiments that are listed. So what
I'm doing is I'm giving you a specific, easy and cheap testable a hypothesis that would confirm or deny their proposals.
Yeah, we could definitely talk more about this, but we want to avoid modifying existing experiments and turning them into new experiments. But if there is a report of such an experiment that has done something, then we'd be very interested in it. Or if somebody else is willing to explore this space and then come back to us with some claims, we could also look into them.
What I'm arguing
we don't have the risk profile where we can innovate on experiments.
What I'm arguing is, it is the process, is what they're saying, and you can test whether they're right or wrong with a simple and cheap addition, just to test whether they're right or wrong. They're arguing it is the process that you are trying to replicate in the original experiments.
Okay, let's chat more about whether that's a good use of time and resources.
Hi, Florian. Thank you for your talk. Do you have any expectations as to what energies of the gammas you would be expecting to see?
Yeah, the gammas, they depend on the decay of these excited metal nuclei based on the hypothesis that we've articulated. So Peter's talk will present quantitatively what kind of energy levels you would expect to be able to absorb this 23.84 MeV or multiples of this, and then what the corresponding decay channels are. And some of these decay channels will include the emission of neutrons, and some of the higher level decay channels will include more symmetric splitting of these nuclei, and some of them will also emit gammas. But yeah.
Thank you.
Yes, a few points quickly. One is about the dates. Mastro Matteo is much earlier than that. He just followed the Narcissus experiment using the STM.
Yeah, I'm aware of that. These are two papers. I put the dates down for two of the papers that were particularly detailed. Yeah. But I'm aware that he already worked on these kind of experiments in the 2000s.
Yes, and one thing I would underline is that at some point you pointed out about the deuterons. Right. But this is one of the experiments, there are not many, where he achieved almost the same results with hydrogen and deuterium. The only difference was one element that was only in the deuterium one. Right. So compare, for instance, we heard this morning, this is a strange thing because a lot of the other experiments only work with deuterium. So understanding that would be an interesting point.
Yeah, I mean, let me comment on this real quick. I mean, of course, in most hydrogen that you buy, there's deuterium present, but then you would still expect a different outcome. But then also Peters also looked at, if you have the helium and deuterium, hydrogen and deuterium as a pair, then you get your 5.5 MeV transition, and so the same principle applies of accelerated, in this case, HD fusion.
But if it were an impurity, I think you would expect them different magnitudes, while they were basically very similar.
Yeah, you would expect different outcomes. Yeah.
And also, I'm not aware of any gammas in the past experiment, so I don't know if you expect them for something, because it looks like you are checking for them because this is what the normal theory would expect.
No, we don't check for because of that, but we check for them because Berdyukov et al. Reported gamma bursts during these kind of experiments.
And finally,
can I pause here? Sorry, you asked a lot of questions. Konrad is still standing there, so you can talk later. Konrad, last short, I hope, question.
My point is, I still don't understand, this large difference between excitation energy of helium-4 in the D system compared to the phonon system. There's, 24 MeV and 100 millielectron. So if you are speaking about strong coupling between two different systems, it will be very difficult to explain it. But this probably we can discuss later. This something.
Yeah, we've created a series of notebooks, Python notebooks, where we use a Python library called QTIP that allows to put together Hamiltonians and time evolve them. And I'd love to send you the links. But so here we can put together simple Dickey models with two-level systems with large energy differences and a very weak coupling. And you can see how the quantum state transfer takes place even if the coupling is smaller, much smaller than the energy, the transition energy, but it takes forever. If you have small coupling, but then you can counter that taking forever by having large Dickey enhancement, and therefore, if you have large Dickey enhancement, then the low coupling energy is kind of compensated by the large Dickey enhancement.
You need for that a lot of neutrons or a lot of atoms consisting together.
So in this calculation, in this back of the envelope calculation, we had 10 to the 12 deuteron pairs, which then gives you large Dickey factors. But Peter will be able to speak on this.
My point is a little bit different. You were speaking about that electron skinning. You should wait many billion years for some. No, the problem is we can explain the reactions we measure with the Kling effect. Very, very nice. So the Kling is much larger, then you will see in our contribution next days. So with screening we can explain very well the nuclear reaction rates and thermal energies. So only the problem is the D reaction, because we have the additional resonance there that can change the branching ratios. But this maybe additionally 10 to 3, 10 to 5 in the amplitude. There is not so much. So
what screening potential would you assume then in EV?
We have measured just new measurement using our accelerator experiment. We have 500 electron volts as a screening energy.
Okay, so we will talk about this later. Thank you for the discussion. Thanks to Florian.